Hello, everyone. I am Ali Badran, and I've been working with Jonathan Kroll from UTA on the topic of in-situ visualization of polymer-to-ceramic conversion using micro-CT imaging. I'm going to quickly go through the motivation, the objectives, as well as describe our segmentation approach for this project. And then I'm going to present some preliminary analysis and what we plan to take these analysis for next steps. So a big part of the PIRE project is focused on polymer-derived ceramics. And like Zung presented, there is a high need for high-strength fibers that are low-cost and stable. And the challenges that go with that is understanding the synthesis and processing, as well as characterizing the mechanical properties of these newly made fibers. PDCs are also a good candidate for the need of matrices and coatings, but the challenges of this is being able to understand the curing and pyrolysis stages to optimize the infiltration methods for matrices. Tomorrow in the invited talks, there are a couple of presentations on the additive sides of PDCs, mainly on understanding the rheology and how to incorporate PDCs in additive methods. But this presentation and this work that I've done with Jonathan throughout the summer will be focused on the polymer matrix infiltration side of things. So before I get started, this work is built on experimental studies that were done part of a PhD thesis by Natalie Larson, advised by Professor Frank Zock at UCSB. And what Natalie did, she focused on studying or visualizing polymer to ceramic conversion. And one of her experiments in the synchrotron involved infiltrating a fiber bed that is surrounded by a glass tube. So she can do in-situ pyrolysis, so she can raise or pyrolyze these polymers in the fiber bed up to 1200 C and cool them down over the course of 20 hours. And within this, she took 90 CT scans within the equally spaced within those 20 hours. And she used this rig here, but not for mechanical testing, but rather for just providing the heating for this sample while being able to CT scan it. So if you've seen my previous work in workshops last year or the year before, I've really focused on looking at the microstructure of 6 CMCs and as well as characterizing the damage. And I've been doing so by image segmentation using deep learning, and that is a paper that is currently in press for the Journal of Material Science. But part of the aims of this project is to be able to apply this work to polymer infiltration studies that could really benefit the PIRE project. So the challenges of these images that were provided by Natalie was that these are images taken across 20 hours with 90 CT scans, and one CT scan provides or generates a 3D image of 2,000 slices. So if you do the math, 90 CT scans is like about 180,000 images. That is 3 terabytes of data that you have to go through to analyze and just even visualize this data. So this is a challenge to the extraction of quantitative information. Another challenge is that after pyrolysis, the matrix and fibers are silicon carbide and they have no gray level difference to them. You can easily see it in the axial cross-section here where you can identify matrices and fibers, maybe pores, but in the longitudinal section, you're really clueless to what you're looking at. So with these difficult images, conventional automated segmentations do not work. So something that can pick up on the features and automate the segmentation process is excellent, and it's part of the objectives here is to automate the segmentation. But what we mean by image segmentation is identifying of different phases of an image automatically. And this identification will help us visualize and quantify the images a little bit more, specifically do analysis on the cracking and void formation due to the constraint shrinkage during pyrolysis in the PIP process. So our approach for this study was to take 14 images at different temperatures and manually segment them. So as you can see here, this is a sample trained image where we go in and go through the manual labor of highlighting the fibers, the voids, the matrices, and the cracks, as you can see here in red. So after these 14 images, we trained one model to be able to identify the phases in the other 90 images. So we used 14 images to identify 180,000 images at different temperatures. And the results here, we just picked up a sample of volume that is scanned at 428 C. And you can see that the model is able to look at the cross-sectional images, label them, and stack them together to visualize the different phases in the longitudinal sections. So these are fibers, matrix, and pores, as well as cracks here that are more clear in the 3D segmented volume. So what can we gain out of this after visualization? A first step that we can do is looking at volume fractions of the different phases. As we've done here for just a sample of 3 different temperatures at 20, 428, and 1200 C. And as you can see here, within the boundaries of error from the segmentation could be better, but as you can see that the fibers are more or less the same volume, but then the matrix is shrinkage as it is expected from pyrolysis, and the cracks are growing. And these experiments here at different temperatures, you can really relate these volume calculations from image segmentation and validate it from the measurements that Natalie has gone through, for example, density measurements, as well as mass percentage loss during pyrolysis. So volume fractions can be useful. The other thing that we can look at is pore volumes and connectivity can be evaluated after segmentation. And as you can see here, the pores can be separated by if they were connected. You can see 3 big volumes of pores here. The red, the blue, and the purple are not connected, but they are big volumes of pores on their own. But what becomes more interesting is when you look at the cross-sectional volume of the pores from throughout the 2,000 slices in one CT scan, you can infer that the amount of polymer infiltrating the fiber bed varies along the length of the specimen. And in this case here, there is less polymers reaching to the bottom of the fiber bed. And this could be either due to the fiber orientation that blocks the infiltration process, or the polymer is viscous and its viscosity limits its transportation throughout the bottom of the fiber beds. Of course, there are more studies and data needed to be conclusive on these claims here, but this is part of the analysis that could be done after segmentation. Another thing to look at is shrinkage cracks. And shrinkage cracks resulting from pyrolysis can give insight to when, where, and which type of cracks occur at different temperatures during pyrolysis. Over here, you can see the 2D view of the cracks, and you can see that there are cracks that are horizontal. This is what Natalie calls the semi-permural cracks, and the cracks that are just connected and wavy. You can see it better after the 3D segmentation over here. But what becomes interesting is that you can evaluate whether these cracks provide sufficient pathways for gas flow during pyrolysis, and also if they provide sufficient subsequent polymer infiltration cycles after this one cycle of PIP infiltration. Another thing to look at here from the cross-sectional slice number versus the volume of the cracks per slice is that better gas escape access is expected at the end, both ends of the specimen, top and bottom. And this allows for faster polymer shrinkage than compared to the middle of the specimen over here. So with all of this studies, there are still yet a lot more analysis that we need to push more. But so far, this method of segmentation has been effective for large CT data sets. And not only that, it allows for feasible quantitative analysis on these images. A big next step for us is being able to identify or define metrics to characterize these connected pathways of porosity and cracking resulting from shrinkage of the polymer. And also, once we have these metrics, we would like to extend these studies to looking at images with multiple infiltration cycles. And after that, it will be very interesting to link this work to what Spencer is presenting next. Spencer is working on nanolayer infiltration, and this is very useful to avoid the issue of shrinkage cracks. And it'll be just interesting to relate the findings of what we have here on the on a bigger scale to what Spencer is doing next. At the time of this recording, I am not sure. Of course, I would like to acknowledge Natalie, Professor Zock, and other people from Dragonfly and the Berkeley lab that had discussions that are effective for this work. But at this point, I'm not sure how we're handling questions over a pre-recorded Zoom. So if you need to email me any questions, please do so at ali.badran@colorado.edu. With that, thank you so much.